Inference about a population proportion usually arises when we study categorical variables. We learn how to construct and interpret confidence intervals for an unknown parameter in Section 2. To estimate the population mean, we record values for the quantitative variable for a sample of individuals. In this section, we'll examine confidence intervals for a population mean mu. Will we ever calculate confidence interval of the mean? Because in 8.2 we didn't have the mean or the standard deviation. But will we ever calculate the confidence interval for a mean when the population standard deviation is known? The answer to that is yes. We call this a one sample Z interval for the population mean. And if you draw a simple random sample of size n from the population having unknown mean, remember that we don't know the mean, but a known standard deviation, as long as the normal and independent conditions are met, a level C confidence interval for mu is x bar plus or minus z star times sigma over the square root of n. And this is going to give us our interval. And our critical value z is going to be found from our standard normal distribution. All right. How can we choose the appropriate sample size? A wise user of statistics never plans data collection without planning the inference at the time. You can arrange to have both a high confidence and small margin of error by taking enough observations. So we have to figure out what sample size we need to take. So how do we choose an appropriate sample size when we plan to calculate the confidence interval for the mean? Okay. Get a reasonable value for the population standard deviation from either an earlier or a pilot study. Earlier study or a pilot study. So if you have the standard deviation, we could add that. Find the critical value Z star from a standard normal curve for a confidence level C. And then we're going to use this formula. Set the expression for the margin of error to be less than or equal to the maximum margin of error, and then solve for n. All right, so here we go. Administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate at the 90% confidence level with a margin of error of at least 30 minutes. A pilot study indicated that the standard deviation of time spent on homework per week is about 154 minutes. How many students need to be surveyed to estimate the mean number of minutes spent on homework per week with a 90% confidence and a margin of error of at most 30? Okay, so here's the problem. How many students need to be surveyed to estimate the mean number of minutes spent on homework per week with 90% confidence and a margin of error of at most 30 minutes? We're going to use this formula. The 1.645 comes from either your calculator or on table A, using 90% confidence. That's 10% with a 5% on the left tail. So 5% on the left tail is 0.05. If you go into your table A and put that in, it's in between 1.64, and 1.65. If you use your calculator, it's going to give you 1.645. 154, and we're trying to find n, and this is our max, at most 30 minutes. So when we solve this, we get n equal, or is greater than or equal to 71.3. So, therefore, the administrators need to survey at least 72 students. Okay, this is just a tip. We rarely, if ever, use Z procedures to calculate a confidence interval for a population mean mu. The only time Z procedures are valid is when the population standard deviation is known. We briefly introduced the one sample Z interval for two reasons. First, to provide a link between the Z intervals we have been using in sections 8.1 and 8.2, and second, to provide a method for estimating the sample size needed to achieve a desired margin of error. If we don't pretend to know the population standard deviation when calculating sample size, we need to use a T critical value. However, to know which T critical value to use, we need to know the degrees of freedom. To know the appropriate number of degrees of freedom, we need to know the sample size, which is what we are trying to find in the first place. Okay, the method that we're using in this textbook for calculating the sample size actually underestimates the sample size needed by using a Z critical value instead of a slightly larger T critical value. However, when the anticipated sample size is large, the difference between Z and T critical values and the difference in the sample size calculations is very small. So what statistic follows a T distribution? Okay. If you draw an SRS of size n from a large population that has a normal distribution with mean mu and standard deviation sigma, the statistic is T equals, this is your sample mean minus your population mean over standard deviation of x over the square root of n. Okay, that has the T distribution with degrees of freedom, df, equal n minus 1. This statistic will have approximately a T distribution as long as the sampling distribution of x bar is close to normal. When do we use the T distribution? We're going to use the T distribution table when working problems when the population standard deviation sigma is not known. So if we don't know the population standard deviation, we're going to use the T distribution. Okay, so describe the shape and center and spread of T distributions. Okay, so what do they look like? Well, the density curves of a T distribution are similar to the shape of standard curve. They are symmetric about zero, single-peaked, and bell-shaped. The spread is a bit larger than that of the standard normal distribution. So we're going to have a wider spread here. And as the degrees of freedom increase, the T density curve approaches the standard normal curve more closely. So if you look at this, the purple represents the standard normal. If we have 2 degrees of freedom, that's our red. But if we have 9 degrees of freedom, it's getting closer and closer and closer to our normal curve. Now you might ask what degrees of freedom are all about. Well, there's no simple answer to that. Simply, the shape and spread of t-distributions depend on the degrees of freedom, which depend on the sample size. The larger the sample size, the more degrees of freedom. The closer the t-distributions come to standard normal distribution. Okay. All right, suppose you wanted to construct a 90% confidence interval for the mean of a normal population based on a simple random sample of size 10. What critical value T star should you use? Using the line for degrees of freedom, 10 minus 1 equal 9, and the column with the tail probability of 0.05, since it's 90 degrees, that's 5 for the left tail. And the desired critical value is T star equal 1.83. Okay, so looking at this, I'm showing you the table. This is table 3, or table T, T distribution. 90, and I come down here to 9 for my degrees of freedom, and 0.05, which is what we should have. So 0.05 is 1.833. If you look down here at the bottom, it actually shows you that that's the 90% confidence level. And our table in our book looks a little bit different than that. It does have the 90 at the bottom. And we're going to use 9 for our degrees of freedom and 1.833. All right, for our T star. If you wanted to construct a 99% confidence interval for using a sample size of 75, using the line for degrees of freedom, 75 minus 1, since that's our sample size, equals 74, and the column for the tail probability of 0.005, the desired t-score is 2.378. And again, I'm getting that from this table, 99 up here to 75, and it doesn't look like it shows 74 on here for me, but I could estimate. And okay, since I can't, it doesn't show 74 in there, I'm going to have to use the calculator to get T. Okay, now would be a good time to stop, check your understanding on page 487. So, we're going to be use table A to find the critical value T star that you would use for a confidence interval for a population mean mu in each of the following situations. If possible, check your answer on technology. So a 98% confidence based on 22 observations. And that is T equal 2.518. A 90% confidence using 10 observations is 1.833. And a 95 confidence interval using size 7 is 2.447. What is the formula for the standard error of the sample mean? How do we interpret this value? And is this formula on the formula sheet? All right. Well, the standard error of the sample mean X bar is S sub X over the square root of N, where S is the sample standard deviation. It describes how far X bar is from mu on average if in repeated simple random samples of size n. So it describes how far X bar will be from mu. Okay, is it on the formula sheet? No, but the standard deviation of X bar is on that, and it's very close to the same thing. Standard deviation of X bar is sigma over the square root of n. So you just need to know which you're using. You'll probably only be given one anyhow, so you'll know what to use. Okay? You're expected to know that it's okay to use S sub x in the formula when the value of sigma is unknown, when the standard deviation of the population is unknown. Okay? Let's move on. Okay. What is the formula for the confidence interval of a population mean? Is this on the formula sheet? Well, there's the formula, X bar plus or minus T star over standard deviation of X, times the standard deviation of X over the square root of n. Is this formula on the formula sheet? And no, it is not on the formula sheet. However, the formula sheet does include the general formula for a confidence interval and the formula for the standard deviation of X bar of a statistic. Okay. What three conditions for constructing the confidence interval for a population mean? Well, random. The data come from a random sample of size n from the population of interest of randomized experiment. This condition is very important. Okay, normal. The population has a normal distribution or a sample size is large. N is greater than 30. And independent. The method for calculating a confidence interval assumes that individual observations are independent. To keep calculations reasonably accurate when we sample without replacement from a finite population, we should check the 10% condition. Verify that the sample size is no more than 1/10 of the population. Administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate at 90% confidence level with a margin of error of at least 30 minutes. A pilot study indicated that standard deviation of time spent on homework per week is about 154 minutes. How many students need to be surveyed to estimate the mean number of minutes spent on homework per week with 90% confidence and a margin of error of at most 30? Okay, well, first of all, we can't do a t-test on this because it's given us what the standard deviation is. So this problem actually gives us a standard deviation, and we won't be able to do a t-distribution with it. So here's the new problem. All right. The principal at a large high school claims that students spend at least 10 hours during the week doing homework on average. To investigate this claim, an AP statistics class selected a random sample of 250 students from their school and asked them how long they spent doing homework during the last week. The sample mean was 10.2 hours. The standard deviation was 4.2. Okay, our problem is to construct and interpret a 95% confidence interval for the mean time that students at this school spent doing homework. And based on this interval, in Part A, what can you conclude about the principal's claim? So, solution. First of all, state. We want to estimate mu, the mean time spent doing homework in the last week for students at this school with 95% confidence. We need a plan. We construct a one-sample T interval provided the following conditions are met. Remember, we have to watch those conditions. Random, the students were randomly selected. Normal, the size is large and equal 250, so it's safe using T procedures. Independent, because we are sampling without replacement, we must check the 10% condition. It is believed that there are at least 10 times 250 or 2,500 students at this large high school. So okay, remember that our degrees of freedom, we take the 250 and minus 1 degrees of freedom, and we want a 95% confidence interval. We use the table T and a conservative degrees of freedom of, that should be of 100, and get this critical value. So let's look at that table. 100 degrees of freedom and 95%. So we get 1.984, and there it is. We put it into the formula, okay? X bar plus or minus T star times the standard deviation of X and over the square root of N. So 10.2 plus or minus 1.984 times 4.2 over the square root of 250. And when we do and work this all out, we get an interval of 9.67 and 10.73. So there's our interval. Should be between 9.67 and 10.73. So we can conclude that we are 95% confident that the interval from 9.67 hours to 10.73 hours captures the true mean number of hours that the students at this school spent doing homework in the last week. Since the interval of plausible values for mu includes numbers that are less than 10, the interval does not provide convincing evidence to support the principal's claim that the students spent at least 10 hours on homework per week on average. So that concludes this lesson.